Okay, so let's start. So last time we saw some basics of probability theory, okay, and randomized QuickSort, and one analysis for that to compute the expected running time of the algorithm. And I had asked, there was another analysis after which I could cover, and I had asked you to kind of go over that in the slides. They were in the slides. So did anyone get a chance to look at it? Too much course load? How many courses you have? Like undergrad? 4, 5? 4? Yeah, a lot. Okay, so today we are going to kind of, what I want to do is, so there were questions at the end of the lecture that, okay, you are doing expected running time, but what if I want the guarantee of running it fast always, or like almost always? Okay, if you are saying expectation is n log n, but most of the time if it is taking much more time and taking n log n with a tiny, tiny probability, then it's of no use, right? So today, by the end of the lecture, I want to kind of convince you that in fact the randomized QuickSort takes almost always n log n. Okay, almost always meaning with 0.999999999 probability. Okay, if your arrays are large. Okay. Okay. So I will go over the slick analysis of randomized QuickSort, which I had asked you to go over. Then we will talk about why, when you have an expectation, most of the probability mass is kind of lying around expectation. Okay, so if your algorithm is taking some expected time, say n log n, then you can almost always prove that with very high probability it will take n log n. Okay, it's not only expectation, almost always it will take n log n time. Okay, and for that we will make use of these 3 types of inequalities. Markov's inequality, Chebyshev, and Chandra. So they are kind of, in terms of how strong they are, it is kind of in increasing order. Okay, we'll see what I mean by that, we'll quantify that. And finally we will do this high probability analysis for QuickSort. Okay, so just let's recall what was the algorithm. So you have an array of n numbers unsorted, right? We pick a pivot at random from these uniformly at random. So picking any element, the probability of picking any element is 1 over n. And then we compare this element with every other element in the array and find out what are the elements smaller than this element and what are the elements bigger than this element. And then put this element, if there are like I minus 1, if this element has ith rank, ith position in the sorted order, then I minus 1 smaller and n minus I bigger elements, right? And then we recursively solve these smaller and bigger sort these smaller and bigger elements. This is fine, right? Okay, so let's say we were using QA to denote the number of comparisons we make in this algorithm, total number of comparisons. Okay, so how many times do we compare 2 elements to check which one is bigger and which one is smaller? Okay, now in the first round, how many comparisons do I make? When I pick the first element, try to find it the smaller element, all the smaller element than this element, and all the bigger element than this element. How many comparisons am I doing? N comparisons at most, right? Actually n minus 1, yeah, doesn't matter. So in every round I'm making some comparison and I want to kind of see how many comparisons do I make. So before we go into this, I want to kind of give you an intuition of why we would get something like n log n. Okay, so any ideas? So suppose I give you some, you have some powers so that you can choose elements so that things are, the partitions are of the size that you want, always. Okay, what kind of element you would want to choose so that the algorithm would run really fast? Middle, right? Because if there is a bias, you are making one of the array very large, and then it may take more and more time. So if you take a middle element, suppose you're actually able to do n over 2, n over 2, then you are reducing the problem size by half, right? If you are unlucky and you make like 0 and n minus 1, then you are just reducing the problem size by 1. And that's really bad. Right? So this middle element, if you are really able to choose the middle element, it will take n log n. Okay? And we will kind of see that you really don't need exactly the middle element. Okay? Somewhat around middle, like between n over 4 and 3n over 4 is good. Okay, some constant fraction is good. Around the middle is good enough. Okay, so that is kind of intuition why you would get n log n. And so suppose I tell you that it's not only that you get n log n when you pick a middle element, but even if you pick a rank n over 4 between some element between n over 4 and 3n over 4, then what is the probability that I will pick such an element in the first round? So I have n elements, right? They all have some rank, some position in the sorted order. Okay, ideally I would like to pick the element which has the position n over 2, so that the true subarrays I get are of size n over 2. Now I say I'm relaxing that. I don't want exactly n over 2, but something which has position n over between position between n over 4 and 3n over 4. So how many elements are like eligible? Half of them, right? So what is the probability that I'll pick one of those elements? 1/2, right? So kind of you have a choice, not only one choice, but like half of the choices are good. Okay, and that is kind of an intuition. Okay, so let's do this analysis. So let's say, so this is a kind of a somewhat, like I would say a simpler analysis. Okay, so because we are counting the number of comparisons, let's define an event when you compare ith rank element with jth rank element. What do I mean by rank? Rank is the position of the element in the sorted order. Okay, so let's define this event Rij, which happens when I compare ith rank element with jth rank element. And let's say xij is indicator variable for this event. So xij becomes 1 during the algorithm if I really compare ith rank element with jth rank element. I'm not going to compare all elements with all other elements, remember, right? Because otherwise I'll get n square. So I'm not comparing some elements. Okay, so xij becomes 1 when I compare ith rank element, that is in the sorted order this element has ith position, with the jth rank element in the sorted order this second element has jth position. Okay, let's see what do I mean by this. Okay, so first of all, the number of comparisons is just the summation of xij. Do you agree with that? Right? Because xij happens only if whenever I compare I with j, and if you sum up over all possible I and j, then that is the total number of comparisons you are making. And by linearity of expectation of the number of comparisons is just that expectation of sum of the expectation of all of these xij. And because this is an indicator random variable, expectation is just the probability of that event. Right? So now the only thing to finish this analysis is to compute this probability of Rij. If we can do this, then we get the expected running time. Okay, and this will also give the worst case expected running time because I didn't make any assumption on the array A. It can be arbitrary input array. Okay, so let's try to compute Rij. So let's see what is happening actually. When does this event happen and when it doesn't happen? Okay, so suppose I have this array. This is unsorted, 7, 5, 9, 1, 3, 4, 8, 6, and this is these elements position in the sorted order. So 1 is the smallest, 3 is the second smallest, 4 is the third smallest, then it's 5, then 6, right, then 7, 8, and then 9. Only 2 is missing in this array. Okay, so it's 1, 3, 4, 5, 6, 7, 8, 9. That's the sorted order. Okay, now let's say my I is 4 and j is 7. Okay, so I want to check whether 5 is going to be compared with 8. What is the probability of that? Okay, now suppose I pick the first pivot and it turns out to be, let's say, 3. What happens then? So 5 and 8 both are smaller than 3, right? So it will be in this round, they are not going to be compared, right? They will be pushed together in all the elements which are bigger than 3. So it will be pushed to a sub-problem. Okay? They will be together in this subarray which contains all the elements bigger than 3. Now you have to ask the same question in this subarray again. Okay, so in the first round, it won't be compared if the first pivot is 3. Suppose the first pivot was 9. Then, again it is pushed into a subproblem. Because 5 and 8 both are smaller than 9. So again, we cannot answer this question in this round, whether it is going to be compared or not. We have to ask again to this subproblem. Right? What if it is 5? The first pivot is 5. Compare, right? Because I'm going to compare 5 with all the other elements to check which one are smaller and which one are bigger. Right? So, great, it will be compared. And once we compare it, they are separated, right? Now, I'm not going to compare 5 and 8 again, ever. Because I'm going to recurse on the subproblems. And so, no more comparison with that. Okay? The same thing if it is the pivot is 8. Right? I will compare 8 with 5 to check whether it's bigger or smaller. It's smaller, so it goes into the subproblem, and again, never I compare 5 and 8. Right? What if it is 6? Do I compare them? In this round, do I compare them? Do I compare them ever? No. Why? Because they go to different subproblems. Right? Because 5 is smaller, 8 is bigger, they go into different subarrays. And when I recurse on the different subarrays, they are never going to be compared because they are different in different problems. Right? So what is the conclusion? You have to be really, really, really lucky to compare them in some sense. Right? In the first round, there are only 2 choice of pivots for which they will be compared in the first round. Okay? But you can push the question to the subproblems. It may happen. So Rij happens if and only if I or j ranked element is the first pivot out of all the elements which are ranked between I and j. That's the conclusion. Right? So if, look at all the elements which have ranked between I and j. First thing we saw is, if you pick any element bigger than that, or any element smaller than, so any element bigger than j and any element smaller than I, then you don't compare in that round. Right? If you pick I or j, then you compare them. If you pick anything in between I and j, then you never compare them. So if, when I pick the first pivot out of these elements between I and j, it has to be I or j. If you pick anything else in between, then you will never compare them. Okay? So let me repeat this. I'm going to kind of prove that this gives a probability of Rij 2 over j minus I plus 1. Let's see how. So in general, let's say we have these n elements. Okay? And let's focus on the set which are and let's say these are in the sorted order. Okay, so once I sort these elements, this is how they look alike, A1 through AN. Okay, and AI has ith rank in the sorted order, and AJ has jth rank in the sorted order. Now focus on all the elements between AI and AJ in this sorted order. Okay. Now, what I just said was that if I pick a pivot which is outside S, then you push the question to a subproblem. Right? If I pick a pivot from S, then AI and AJ are going to be separated. So this is the first pivot I am picking from S. First time I am picking a pivot from this set S during my algorithm. So far I have been picking pivots from outside S. Okay, and I was pushing this question in the subproblems. Okay, now this is the first time I picked the pivot from S. Okay, now AI and AJ may be compared, but once they are compared, they will never be compared again. And they will be compared if and only if this pivot that I picked from S is either AI or AJ. For any other choice, I'm not going to compare them. Right? So what am I saying? I'm saying that AI is compared with AJ if and only if the first chosen pivot from S is AI or AJ. Okay, so imagine that you are running this algorithm and you are also looking at the subproblem in every recursion level. So far, up to some level, you have never picked a pivot from this set S. Okay? Now, at some sublevel, in some subarray, suddenly you pick a pivot from S. Okay? If it is AI or AJ, then you compare them. If it is not AI or AJ, then you will never compare them, ever, during the algorithm. Okay? So condition on the fact that you pick a pivot from S, the probability that AI and AJ will be compared is 2 divided by size of S, because I'm picking a pivot uniformly at random, and it is from S, I know. Right? So there are size of S elements possible when I pick that pivot, but I picked AI or AJ. So that's 2. So that's why 2 divided by size of S. Questions? What is S that is clear? In that example, what was S? So I had 1, 3, 4, 5, 6, 7, 8, 9. Those were the numbers. And my I was 5 and J was 8. What is S there?
5, 6, 7, 8.
Good, 5, 6, 7, 8. So you are with me, right? Out of 5, 6, 7, 8, so suppose I tell you that, okay, at this point I'm going to I picked a pivot from 5, 6, 7, 8. What is the probability that I picked 5 or 8? Half, right? Because there are 4 elements in the set. Given that I picked an element from this set, I have only 2 choices when I make that comparison. So 2 over 4 is half. Okay? So if I put everything together, let's say E is the event when I first pick an element from set S. Then what I have so far is that if E happens, given that E happens, I and J are compared with probability 2 over J minus I plus 1, because size of S is J minus I plus 1. Okay, but this is a conditional probability. Okay, it is saying that conditioned on E happening, probability of Rij is 2 over J minus I plus 1. But what is the probability of E happening? Throughout the algorithm, not in one round. During the algorithm, what is the probability that E will happen? 1, right? Because if E doesn't happen, how would I sort the elements which are between AI and AJ? So when does the algorithm stop? What is the stopping condition? I never said that. Of course, when the array is sorted, right? But we know that, yeah, everything is sorted, you're right, right? But when do I know that, yes, everything is sorted now? I don't want to kind of check in every round, whether it's sorted or not. In the recursion, I have to provide a stopping condition, right? That you do not recurse anymore if, exactly. If the array you provide me in the function has only one element, right? Now, if I have this set S, and every time you provide me an array which has set S intact, right? That's when E hasn't happened. And I know that set S has at least 2 elements, AI and AJ. So it's not going to stop. The algorithm is going to recurse on that, right? So the probability of E happening is 1. So that's why we get that probability of Rij is actually 2 divided by J minus I plus 1. Okay, this is the most important point. After this, it's just algebra. Okay, so questions. Did you see? I mean, the analysis is completely different. I mean, the events we defined, the random variables we defined are completely different. Okay, we made a heavy use of indicator random variables. We focused on exactly the event that we want to count, right? And made that a random variable out of that. When does 2 elements get compared? Okay. So now we have this. So then we just want to sum these numbers for I less than j and between 1 and n, right? So it's just, this was the expected number of comparisons I'm making. And the formula is the summation of p Rij for I less than j. And that just replace what is the probability of Rij, that's 2 over j minus I plus 1. Okay, and I can simplify this summation, I mean break it. So I goes from 1 to n minus 1 and then j at least I from j through n. Right? And the same number, I can just rewrite that as what is this value? When j is I plus 1, it is 2. Right? And up when j is n, it's n minus I plus 1. So delta going from, instead of this summation, I'm just saying delta going from 2 to n minus I plus 1, 1 over delta. Okay? And does this second summation look familiar? It's a harmonic number. Okay? Minus 1, but that doesn't matter. You can just remove that. And yeah, we get summation of these harmonic numbers. If you don't know, it's just Hn is 1 plus 1 over 2 plus 1 over 3 plus 1 over up to 1 over n. Okay? And that's kind of theta log n. And because we are kind of adding n harmonic numbers, we get nhn, so n log n. As I said, the main important part is to compute the probability of Rij. After that, things will follow. Okay. No questions. Okay, so now I want to switch to the inequalities that I talked about, which would help us to prove kind of, so far we have been computing expectation, and now suppose we want to compute, oops, sorry. With high probability. We want to kind of prove that randomized QuickSort takes n log n time with high probability. Almost always it takes n log n time. Okay. Okay. Two noises, two voices. So listen to me and not that. Okay. So let's suppose I'm flipping n coins. Okay. So the question is, when we talk about expectation, how good is that an estimate in terms of when the value has the expected value? Okay. So suppose you are flipping a coin n times, okay, and let's say heads is 1 and tail is 0. And you ask, how many ones am I going to get? Okay. This is kind of a binomial distribution. So suppose I toss it 2 times. Then with half probability, I get 1 head. Right? With 1/4, I get 0, and with 1/4, I get 2. Good? Okay. As I increase n, this curve becomes more and more like a mountain, more like it will have a sharper and sharper peak at mean. Okay? So if I do it 4 times, then the mean is 2, right? Expectation is 2. Every time with half probability I'll get head, right? So expectation is 4 times half is 2, right? And as you go away from the mean, the probability decreases. Okay, and as you now increase the number of trials, it really decreases sharply. Okay, so it really starts looking like expectation is the real thing, right? All the probability mass is at the around the expected value. Okay, and this is what we want to kind of prove quantitatively. Okay, this is for a very specific type of distribution. We are just flipping coins. Okay, so this is called concentration of mass around the mean. Okay, and it's also called law of large numbers. It's exactly what I just said. So almost all the probability is kind of concentrated around the expected value. Okay, so that's what the law of large numbers says, that for large n, the middle portion of the binomial distribution, this is called binomial distribution because we are, it's kind of independent, the same event is happening independently in every round, and it looks like this normal Gaussian distribution where there is a huge amount of mass near the mean. Okay. And that's why the randomized algorithm, when we kind of talk about expected running time, it's not like unpredictable in that sense. I mean, expected running time is what happens almost always. Okay. And we will use these some well-known inequalities to kind of prove this quantitatively. And let's see which kind of inequalities. Okay, so let's say we want to do this very simple analysis of QuickSort. Again, we want to count the number of comparisons made. And suppose I can tell you that C is the upper bound on the probability that the number of comparisons is, say, 10 log n, 10n log n. Okay, and with 1 minus C, it is actually, so the number of comparisons which are more than order on n log n, that probability is bounded by C. Okay, if C is very, very tiny, we are very happy. Because with 1 minus C, your running time is n log n, that's what we wanted. If C is very, very tiny, 1 minus C will be very, very large. Okay. And this will also give us some formula for the upper bound for the expected running time. So again, it will be this n log n, order n log n, plus some n square term times C. But if again the C is very, very small, then this term will not matter. Okay. So the main question is, how do you bound this probability? How do we compute this C? That is the main question. Basically, you are computing the probability that is, what is the probability that you will be away from the mean? Okay, if you can bound that, like we saw in the distribution in the picture, right? That probability was going smaller and smaller and smaller. All the mass was at the mean, the probability mass. Okay, so the first inequality is Markov's inequality. This is a very simple to obtain. This says that if x is a non-negative random variable, this is important, then for any number a, probability that x is greater than or equals a is expected value of x divided by a. Let's see how do we get this. So just is a simple way to look at the expectation. So look at the expected, this formula for expected value of x. What is that formula? Take every element in the probability space and then multiply sum over every element in the probability space, multiply the probability of that element times the value you get for x. You are just averaging, you are looking at the average value of x, right? Now this is at least, suppose I look at only those elements where this value is at least a, because that's what I am interested in. Okay, forget about all other elements. Now this is greater than or equals because x is non-negative. If x was negative, can I say this greater than or equals? No, right? Because when x is non-negative, when I go from here to here, I am removing some positive values from here, the summation. But if x had negative values, I may remove negative elements, and that may switch the inequality. Right? So all these x omega are at least a. So let me just pull out a instead. So replace this x omega by a, and that will make it again this value greater than or equals, right? Pull out a, and then we are left with this, but this is exactly, you are counting the probability of elements when the element has at least a value in the random variable. That is exactly the probability that x is greater than or equals a, right? And you bring this a in the denominator here, like divide both sides by a, then you get probability of x greater than or equals a is expectation of x divided by a. Simple. This is, if you don't like algebra, this is the proof by picture. Suppose I am plotting the value, all possible values of the random variable, and on the y-axis I am plotting what is the probability that random variable has value at least x, small x. Okay? When x is 0, because my random variable is non-negative, the probability is 1. And it has some maximum value. I don't know what. I don't care. Okay? The area under this curve is exactly the expectation of x. Right? Because what do you do when you compute the area? For every point, you kind of take a small bar here, right? And you multiply, you can kind of divide this entire area into small, small bars, and those are like exactly x times probability of x equals x. Right? And suppose I have this a here, then this value is exactly probability that x is greater than or equals a. So this area of this square is a times probability x greater than or equals a. But this red area is less than the black area, of course, right? So you get the inequality. Okay, let's apply this. So suppose I have a bag. It has black and white balls. Okay, there are n balls. Okay, and there is some fraction of black balls. I want to estimate that fraction. How many black? What is the fraction of black balls in the bin? So what can I do? How do I do that? I don't know this p star, the fraction of black balls. Okay, sample, right? That's the thing we do always, sample, right? So suppose I sample with replacement. So I sample, look at the color, say like put a bar, if it's black, put it back. Again sample, again look at the color, put a bar, if it is black, put it back, and then count the number of bars. Okay? Now I want to do as good an estimate as possible. So if suppose I'm going to do this, and suppose I sampled k, and out of that b are black, then I'm going to say p is b over k. That's a good enough strategy, right? Yeah.
Why we sample with replacement?
Good question. Because it makes analysis easier. So suppose I have two balls. Okay? And let's say one of them is black, I know that. Okay? Now when you sample the first time, what is the probability that you will get a black? So p star is half. What is the probability that I get black? The question is clear. I have only two balls in the bin. One is black, one is white. You don't know that, but I know. Okay? So p star is half. The number of balls, the fraction of balls in the black balls in the bin are half. Now I sample. I mean you sample. Right? What is the probability that you will get a black one? 0? Half. Right? With half probability you will pick a black one. With half probability you may pick a white one. right? Suppose you pick a white one. Now again you sample and you don't put it back. Okay, you put it aside. Now you sample. What is the probability that it will be black? 1. Right? So it changes the probability. And in this simple case, it seems easy to kind of analyze. But if you have like a million balls and you want to do this analysis, it changes the probability of getting a black. And that makes the analysis difficult. And that's why you kind of generally do with replacement. It improves your estimate for sure if you do without replacement. But it's difficult to argue in general, even in algorithms. Okay, so what I want to do is I want to get my estimate as close as P star. Okay, I may output more than P star, or I may output less than P star actually. Okay, so what should be the K? How many samples should I do so that my estimate is good enough? Okay, that's the question. Okay, the setting is clear. So in this example of 2 balls, if I'm going to sample only one of them, if I sample it and if I get like one, if it is black, then I'll say 1, P is 1. If it is white, I'm going to say P is 0. If I'm going to sample only one ball, if K is 1. Okay, setting is clear? Okay, so I want to prove that my estimate is more than 2 P star, 2 times actual fraction. Probability of that is at most half. Okay, so I may be away from P star, from the mean. P star is the mean, actual mean. Right? That is the actual fraction of black balls in the bin. 1 minus P star fraction is white. Okay? So let's define a random variable, say xi, okay, which is 1 if I'm going to do k samples. Okay, that's fixed. I'm fixing that. Okay, some number, k greater than 1, at least 1. Okay. Let's say xi is 1 if ith ball is black, otherwise it's 0. Then what is the expectation of xi? It's P star, right? Because of with replacement condition. Ith sample is no different from the first sample. Is this point clear? Why is that? Every sample is the same. Expectation of getting black in every sample is the same. It's P star. Why? The distribution of black balls is not changing, right? The fraction of black balls in the bin is always the same because I'm going to put the ball back in the bin. So every sample is independent in that sense. It's not affecting other sample. Okay? So what is the number of black balls? That is exactly summation of xi's. The number of black balls I see is exactly summation of xi because xi is 1 only when the ith ball is black. right? And by linearity of expectation, expectation of B is exactly k times expectation, the summation of expectation of Xi's. And expectation of Xi is P star. So that is exactly k times P star because I'm summing up k expectations. Right? And recall that P was B over K. This is what I'm going to output. Okay? So now I want to compute this probability. Right? Probability, what is the probability that P is at least 2P star? So my estimate is really, really bad in that sense. Like it's twice the actual fraction. What is that probability? So let's just replace P by B over K because that's what it is. And then multiply both sides by K. So the probabilities don't change, right? I'm just doing some algebra inside. So B is the expected, the actual value of this random variable, right? It's greater than or equals to Kp star, but Kp star is expectation of B, right? So what was the Markov's inequality? Markov's inequality, for that just set A equals 2 times expectation of B, right? So the inequality was probability of B greater than or equals A is 1 over expectation of B over A. So Markov's inequality was right, and here A is 2 times expectation of B. So you see, you just replace A by 2 times expectation of B and you get half. Okay. So this is kind of saying that if for your B, if the curve, how do I get new page? I don't know. So if I have this as my random variable, value all possible values of the random variable B, okay, and here is the kind of probability, then if this is the expectation P star, and if this is 2P star, the probability that I am kind of here somewhere, okay, its drawing is not very effective, but it's saying that it's less than or equals half to be in this area, my estimate being in this area. Okay. Okay. So next is the Chebyshev inequality. For that, it talks about how far the value of the random variable that you see is from the expectation. Sorry, there is a typo here. So for that, it's called variance, variance of x. How much does your random variable vary from the mean? It's a measure of that. Okay, so x minus e, expectation of x is how much it is differing, and I am taking a square because I want to look at the mod of that, the amount of variance. Okay, even if it is going down less than the expected value, I want to count that as positive because this is a bad event happening. your value of the random variable is differing from the expected value. Okay? And expectation of that is called variance of the random variable. Okay? So this is the actual definition, but it is always written like that. And let's see why. So let's say y is a random variable which captures this quantity, x minus expectation of x square, for some other random variable x. If I open this up, then I get x square minus 2x expectation of x plus expectation of x square. Right? I'm just opening this up. And then the variance is just the expectation of y, which is just expectation of this term. But by linearity, I can push the expectation and say that it's just expectation of x square minus, what is the expectation of this? Why is it this quantity, 2 expectation of x square?
The expectation of x is just a number. So.
Exactly. Because 2 times expectation of x is just a number. Right? You're just taking expectation of x there. And this, and then it simplifies to this. Okay, first time when I saw variance, whenever I search on Google variance, I directly see this. Okay, and I always wondered, how do you get this? Okay, so it's very simple. You just take the expectation of this quantity, which is actually capturing the variance. Okay, and you get exactly this. I also need somehow the independence of random variables. So x and y are called mutually independent if for any possible value of x and y, probability of x getting this small x and y getting this small y is just the product of the probability that x is x, small x, and capital Y is y. Okay? If this happens for all x, y, then we say that these two random variables are independent. This is exactly, almost exactly same as independence of events. Okay? And whenever two variables are independent, we get that variance of x plus y is just the sum of the variance. Okay? Kind of variance behave like expectation, linearity of expectation. And expectation of the product of the two variable is just product of the expectations. Okay? So we will use this in the example. Okay? So let me now state the inequality. So this inequality is stronger than Markov. Okay? Now it is saying that give me any a, then the probability of x minus expectation of x mod of that is at least a, is at most variance of x over a square. So first of all, this quantity is kind of larger than the quantity we were looking at in the Markov's inequality. Why? In Markov's inequality, we asked whether x is at least a, and we can ask whether x is at least expectation of x plus some number. Okay? So there we were kind of asking what is the probability that you are above the expectation in some sense. Like you are really, your estimate is really more than expectation. What does this say? When you take a mod, what are you, there's something more that you are kind of bounding. What is that? What is mod of x minus e of x? Like, what are these points like? Is greater than or equals a. What kind of x will kind of satisfy this condition? What values of x will satisfy this condition? Exactly. So now you are kind of bounding probability on both sides. values which are really, really bigger than expectation, values which are really, really smaller than expectation. Right? When you take a mod, you bound the probability of bad events on both sides. Okay? And that probability is bounded by variance of x divided by a square. Okay? And we will derive this via Markov's inequality actually. Okay? So let's say again y is the random variable which captures the variance. Okay? It is a positive, non-negative random variable. It should be non-negative here, sorry. Right? So we can apply Markov's inequality. Right? So suppose we apply it for a square instead of a, then y at least a square is at most expectation of y over a square. This was Markov's inequality. Right? But what is, if you replace y at both places, then this is this quantity, and expectation of y is at least exactly variance. We just saw that. Right? And why do I get from here to here? So here I am kind of bounding the probability that x minus expectation of x the whole square is at least a square. But here it's mod. And it's on the right hand side it's a. So every time this happens, this also is just taking a square root on both sides. Right? So every time you get a yes for this inequality, you get a yes for this inequality as well, and vice versa. Right? So these two quantities are same, and that's why you get this inequality. Okay, simple application of Markov's inequality gives us Chebyshev inequality. But we will see why this is stronger, why this is more helpful. Okay. The other incarnation of this is, as we just discussed, right, that this is actually also bounding the probability that the random variable takes smaller value, I mean it's away in the smaller side than expectation. Okay, it is bounding that as well as it is bounding the bigger side. Actually, it is not only this individual inequalities, but also a plus here. So you can say that this plus this is less than or equals variance of x divided by a square. That is exactly the yes. That's the meaning of mod. Okay, so it's in picture. It's kind of bounding, if this is the mean, and this is, say, p star minus a and p star plus a, then it's bounding the probability here and here, the sum of that. Okay, so let's continue with that example. Okay, n balls in a bin, I'm going to pick k out of that. If b turns out to be black, I'm going to say the fraction of black balls is b over k. And the actual estimate is p star. I don't know what p star is. Okay, but I want to estimate it as closely as possible. So if I draw k balls out of it, then I claim that my estimate is, and for any epsilon, my estimate is kind of more bad than epsilon. That probability is bounded by 1 over k epsilon square. Okay, and I'm going to prove it through Chebyshev. This is a much, much stronger statement than the previous statement. What was the previous statement with the Markov? With Markov, I just said that whatever samples you make, doesn't matter how many, what is k? My estimate is more than 2p star, that probability is at most half. So it was completely independent of the number of samples. And that is kind of one weakness of that statement, right? Even though if you make one draw or you make 1,000 draws, okay, it doesn't improve your probability. But here, suppose my epsilon is 0.1, okay, and I want 99%, with 99% I want to be kind of almost p star. I want to be between p star minus epsilon, p star plus epsilon. How many draws should I make? The question is clear? So epsilon is 0.1, okay. So I want to be between p star minus 0.1 and p star plus 0.1 with probability 99.99. So 1 over k epsilon square should be 0.01. Right? Epsilon is 0.1. What should be k? $10,000. Right? And if I make k 1 million, then what will be the failure probability? Kind of, my estimate is like not near epsilon. Or what is the success probability? Sorry? 0.99? 0.9999. Right? Because 10k is 10 to the 6 times 0.01. That is 1 over 10,000. That is 0.0001. Right? And 1 minus of that is 0.9999. So the point is that if you want to increase this probability here, the only thing you need to do is increase k. Which Markov's inequality didn't allow you, kind of, to increase your probability by more and more samples. Okay? So let's prove it. So again, the same setup, xi is 1 if ith ball is black, otherwise 0. And b is the summation of xi, that's exactly the number of black balls you see. And expectation of xi is p star because that's the actual fraction of the black balls in the bin, which you don't know, of course. And by linearity of expectation of b will be kp star. Okay? And the estimate we output was b over k, actually. And the variance of xi is this quantity. Now here expectation of xi square. So this value I know, it's p star square, right? But it's just expectation of xi square is p star square. What is the expectation of xi square? What is xi? What are its values, possible values? 0 and 1. If I square it, what are its possible values? 0 and 1. So whenever it was 1, it still remains 1. Whenever it was 0, it still remains 0. Right? So expectation is not going to change. So for binary random variables, expectation of xi star is just expectation of xi. Expectation of xi square is just expectation of xi. Okay? And so we get that variance is p star times 1 minus p star. Okay? And because these random variables are independent, we also get that variance of, and remember for independent random variables, I said that the variance behaves like expectation. So variance of the sum of the variables is just sum of the variances. Okay? So variance of B will be just summation of variance of all xi, and that is just k times, because there are k of them, it's k times p star 1 minus p star. Okay? You can prove this for binary random variable even without using independence, and you can try it. Okay? So now let's just look at this quantity, which is the p is b over k, so I just replaced it here, and multiply again both sides by k. So I get this, and kp star is exactly the expectation of B, right, here. And that is at least k epsilon is variance. Remember, what was the inequality? It just says variance of x divided by a square. So that is variance of B divided by this quantity, the square of this quantity. That is k square epsilon square. And when you simplify it, you get 1 over k epsilon square. Okay, once you set the right set of random variables, the rest becomes algebra actually. So all the ingenuity goes into setting up right set of random variables. Okay, so this is nice. Now the last inequality, Chernoff bound. Here I really need that binary random variables and they are independent. Okay? So I have, let's say x1, so inequality itself is for this setting. So I have some k random variables, say. They are independent and they are binary. xi is 1 or 0, and 1 with probability pi, and 0 with probability 1 minus pi. Okay? And then let's say I define x, which is a summation of these binary random variables, and let's say mu is the expectation of x. Okay, so all of these is given already to me. Okay, and let's pick a number between 0 and 1, which is delta. Then probability of this x, big X, which is summation of xi, deviates from its mean, mu, by at least delta times mu. So it's a multiplicative factor here, error factor, not absolute. Okay? That probability is bounded by 2 times e to the minus delta square mu over 3. Okay, this looks very weird and it's scary, right? But it's not. And so when I open this up, again, because of the mod, I can rewrite this inequality for the positive side as this. So positive multiplicative error 1 plus delta times mu is at most this value, and from the negative side is this value. Okay. Now how do we compare Chebyshev with this? Like, why is this better than Chebyshev? In Chebyshev, I had a here, and here it was variance of x divided by a square. So variance, so for delta mu, it will be variance of x. For Chebyshev, I'll be getting variance of x divided by delta square mu square. And let's say I know that this is at most expectation, so that is a mu so 1 mu cancels. So 1 over delta square mu. So how do these two quantities compare? Let's say in terms of delta. Which one is better? This is kind of quadratically dependent on delta, right? And this is exponentially dependent on delta. Right? So in that sense, it's a huge difference. Okay? And I'm not doing proof because it's not that one line or two line proof. Okay? You can go over the notes and see, and if you have questions, I can answer them in office hours. Okay? But let's say application of this on our example. Let's just finish that part. Okay? That's simple. Again, the same setting, xi random variable, 1 if ith ball is black and 0 otherwise, and b is the summation of xi's, and expectations we know. Now again we are asking the same question. What is the probability that p minus p star is greater than or equal to epsilon? Replace p by b over k, multiply them, so we get this setting. Okay, so here it's k epsilon. But I need to get a mu here. Mu is just expectation of b, which is kp star. So I multiply p star and divide it. Okay? Because to apply the inequality, I need here mu delta times mu. So mu is this, kp star. Okay? So the delta is epsilon over p star. Okay? Now apply Chernoff. So the Chernoff, I'm not going back because we are running out of time. But it will give you this expression. If you just replace delta by epsilon over p square and mu by kp star. Okay, you will get this expression. And that will simplify to this. Okay, but p star is, because p star is less than or equals 1, it is at most, this quantity is at most 2 times e to the minus k epsilon square over 3. Now previously, as you increase k, your probability kind of bad event decreased linearly, remember? K over 1 over k epsilon square was the probability in that example. Okay? Here it is decreasing exponentially as you increase number of samples. Okay? So if I put all three together using Markov, Chebyshev and Chernoff, Markov didn't say anything about the number of samples that you make. It didn't improve the estimate. Chebyshev did, but linearly with number of samples. But Chernoff exponentially fast. Okay? And that's why kind of, so, but what is the issue with Chernoff? I mean, okay, it's good, right? It's exponentially good in some sense, but there is some issue. Yes, what? Sorry? Mutual independence, right? You need mutual independence of xi's. Then only you can apply it. And that's the caveat. So that's why you need Chebyshev also. And okay, so then again, we'll do this high probability analysis for QuickSort next time. Yeah.
About the INJ comparison,
Uh-huh.
the observation